In the previous video, we started to do some volume calculations, right? And we created this case 1. That's our first volume calculation results. These are stored inside the case 1. And we looked at different ways of computing the volume height maps, and then how to actually display them in a kind of a meaningful way, right? And so now we have a folder called case 1 in our cases tab, right? And then if we click on the results tab, we'll be able to see this volumetric folder that's inside of the results tab. The next thing that we might want to do is to actually try to find out some of the uncertainties of our calculation. And we also have a button that allows us to do that. Right? It's called uncertainty and optimization. Right? So it's right next to the volume calculation. So a natural next step for doing the volume after doing the volume calculation is just doing this uncertainty and optimization step. Let's click on it. Again, it's asking us if we want to create a new one or edit existing ones, but we don't really have a existing one. So here, create a new becomes mandatory. So we can change the name here. We can change it to some other name, say uncertainty analysis, uncertainty case 1. Uncertainty analysis case 1. Right, and then the task for our analysis is going to be sensitivity by variable. Right, it's kind of a default value, right? But if you click on it, you have some other options, right? We can try to explore those those different options, but let's not try to do that in this particular video. Let's just use the default sensitivity by variables. So what this thing actually means is that it's going to allow us to actually specify a certain kind of a range of some of the key variables that are used in our volume calculation, right? And then it's going to run multiple volume calculation workflows with different samples of those key variables, and then we will be able to actually find out if those variables are indeed, if the results of the calculation are indeed very sensitive to those selected variables. And then we have to specify the base case, right? So all those kind of different values, or all those different kind of samples of the variables are going to be based upon this particular base case. So if we don't have a base case, if we have no base case, then this button is going to be grayed out, right? We won't be able to actually do this kind of uncertainty analysis, right? But now we have a case that's already been computed. We can just select it from the case tab and then use this blue arrow to point it in there. So it's telling us that it's possible that this base case will be modified during this kind of analysis process, right? It's asking us if we want to keep a copy, right? Maybe that's a good idea, right? If we sort of make a copy of it and then just do this kind of uncertainty analysis on that particular copy, so we can still keep the original. It's just giving us a warning message, but we're just going to ignore this, right? Because this case 1 is a sort of kind of a test case. Also, it's there's no need to actually sort of keep a copy of it. Now, case 1 is selected as the base case, right? As soon as we have selected case 1, we're going to see all the different steps that we have gone through, right? So the last step is at step 12, which is the volume calculation. And this volume calculation actually created case 1, right? And all those things that's listed here from 3D grid, right? With 3D grid, which is where we actually created the 3D demo grid in our model, right? Our 3D demo grid. And then make horizons and make zones, make layering, and then make contacts, geometric modeling, scale up wheel locks, porosity, that kind of thing. All those steps are listed here, right? And we can actually try to make any of those, make the variables in any of those processes or steps some kind of we can assign a certain range of trial values for those variables, right? Suppose let's look at the phases modeling, right? If we double click on it, it's going to open up the dialog box we used when we actually were doing the phases modeling, actually, right? And this dialog box was actually sort of identical to the dialog box we got when we clicked on the phases, on this phases button, right? And then we also got all our parameters that's set up for different regions also, right? So for top Eve to NIS 1, that's object modeling, right? But we have a zone that's using a sequential indicator simulation, right? And then for this particular setup, we have that's crevice splay, right? Let's look at the background flat plane. So if we look at the background flat plane, we have a variogram that's associated with the distribution, right? With the background flat plane distribution. And for now, we have a major direction that's fixed at 5,000, and then a minor direction that's fixed at 500. So now let's change the major direction and the minor direction into a variable, right? So how do we actually specify a variable? We use the $sign. $sign followed by the name of the variable. Let's call it major range. And then we do the same thing for the minor range, $sign. Right. So now we have specified two variables, right? So everything that starts with the $sign is actually a variable. Once we have defined these two variables, and then we can go back to the uncertainty analysis dialog box to actually specify the range, to specify the distribution of the values for those variables. And then this uncertainty analysis is going to allow us to actually run multiple simulations based upon a specific distribution for those variables. Let's just click on OK. And now we can see there are two variables that's in front of this particular item, right? That's major range and minor range, right? And then we have 3 checkboxes that's checked, right? Because once we change this particular step, all the following steps must be recomputed, right? In the petrophysical modeling, we're using phases model as some kind of conditioning, right? And then in the volume calculations, we're using petrophysical model. So once we change a particular step, all the following steps must be recomputed, right? And that's inside of this base case tab. That's inside of the base case tab, right? And then if we click on variables, now we have 2 items, 2 rows underneath the variables tab. So we'll be doing this kind of uncertainty analysis for these 2 particular variables that we have defined, right? And then if we double click on it, on these icons, it's going to bring up the dialog box that we just saw, right? That's this particular dialog box, right? And where we specified the major range and the minor range variables. Let's close it, right? And these 2 boxes is gonna sort of, because for now these values are actually integers, right? 5,700, these are integers. If you want to confine your sampling of those values, of those variables into like into integers instead of floating point numbers or real numbers, then you can sort of check these boxes. But we are not going to do that, right? And then the base value, that's the value that's used for computing case one, right? That's 5,700, right? And then we can specify the specific distribution, right? By default, it's a uniform distribution. So it's going to be a uniform distribution, and then Petrel is going to draw random values from that particular uniform distribution, right? And you can specify the mean and the max values from that uniform distribution. And Petrel is going to draw random samples from that distribution for major range, right? But let's try to change it. Suppose let's change it to triangular, right? So we're going to specify a triangular distribution, right? And then a mean value, a mode. Mode is actually where the probability is highest, and then the maximum, right? So the mean, let's give it like 4,000. And then the mode, let's give it like 5,000. And then the max is like, let's give it 6,000, right? But it doesn't have to be symmetric. It can be sort of anything. Like maybe it's not a good idea to use maybe minimum, let's give it like 35,000 or something. 35,000. And then it doesn't have to be symmetric. It can be any kind of triangular distribution. It doesn't really matter. And then for minor range, let's use a different distribution. Let's use a normal distribution. Right? And then all we have to do is to specify the mean and the standard deviation. Let's give it like 700 as the mean. And then the standard deviation, let's give it like 100 or something. Right. And that's all we need to do for the variables tab. Right? And then sensitivity. So how many? So number of samples, that's 5 samples per variable, right? But we have 2 variables, so the total number of simulations is going to be 10. Right? It's basically the number of variables multiply the number of samples per variable, right? And the sampling method equals space sampling, but you can sort of maybe Monte Carlo sampler. You can have different ways of sampling the particular distribution, right? You can choose any one that you would like to use. And then add the results to, do we want to sort of do a folder, or let's just use a folder, right? And then at this point, we can sort of click on test just to make sure that the workflow is correct. So test OK. Test OK means that everything that's listed in here, or at least those checked steps, can actually run without any kind of problems. So there's no bug in our program, basically, right? And so if test actually runs, test is OK, then we can click on run. And then it's going to do 10 simulations or do 10 volume calculations. And each time it's going to draw a different major range and minor range values from the distribution that we have specified, right? So let's click on run. And then we're going to be able to actually see the progress of the simulation from the status bar, and it's telling us it's running. So it's going to take a while to actually run through the 10 simulations. On my computer, it's probably using upscale cells for zone-based quotidian total. One defined value in upscale cell likely fail or give bad results. Yeah, it's too old. It's just the years too old. Maybe this is the bad kind of example, right? I didn't actually test this example beforehand. It's basically just saying that the number of data points is like too few, so not enough data points. But it's just for demonstration purposes, we can sort of see if it's going to give us some kind of sensible results. Again, it's a slow computer, so that's why it's taking so long. On a faster computer, this kind of calculation can be done in like a very small amount of time. Okay, so now it looks like it's oh, it's not done yet. It's still running. I probably should have used the petrophysical modeling to set a variable inside of the petrophysical modeling, right? Because those porosity curves actually has a lot more data points than the phases logs. So after this demonstration is completed, we're gonna do the data analysis button. Let's take a look at what's actually inside of this particular data analysis dialog box. The data analysis process is extremely time consuming, actually, right? But the basic purpose for the time data analysis step is to actually find out estimate two things. Basically, the distribution or the fraction or percentages of different kinds of phases, that kind of thing. And then another thing that's important is the variogram. We need to estimate the parameters of the variogram. And it's important for us to actually have some basic understanding about geostatistics, right? So a basic assumption in geostatistics is basically the so-called stationary assumption. The stationary assumption is basically just assuming that the property within a particular zone and then a particular phase is more or less can be treated as some kind of normal distribution, and then the kind of changes within that particular zone and a particular phase can be modeled as some kind of a perturbation or some kind of deviation from a kind of a normal value, from some kind of typical value, that kind of thing, right? This kind of stationary assumption is quite expensive, actually. So in practice, it's something that we need to actually we need to actually sort of, the reason that we divide our entire three-dimensional model into like multiple zones and then multiply and then multiple phases is just to satisfy the stationary assumption, right? So if we treat the entire model as some kind of a one model, then the stationary assumption doesn't actually apply. So that's why we need to divide it into like multiple zones and multiple phases. Now the simulation has completed. Let's just click on OK to close the dialog box. Now we can sort of look at what's actually underneath the cases tab, and then what's actually underneath the results tab. So underneath the cases tab, we still have like case one, but we have an uncertainty analysis case one here. That's like a case folder, right? A case folder contains lots of different cases, right? That's for variable major range, and then we have like 5 different values. And then that's for minor range. Again, we have like a different values, right? If we right click on it and show variables spreadsheet, and then we can actually look at what's actually the values that was taken during the simulation, right? So for case 1 to 5, the minor range was fixed at 700, and then the major range was drawn from that triangular distribution, right? All those random values you can find. You can see they are actually random values, right? And then for case 6 to 10, the major range was fixed at 5,000, and then the minor range actually is drawn from that normal distribution that we specified, right? So that was those are actually the minor range. Those are actually the minor range values used in those simulations, right? So one of the things that we might want to try to do is to just click on the create a sensitivity plot. It's a kind of histogram plot, right? But let's not use this button, but instead let's use something else. So first we're going to create a histogram window by using this Windows button. So now we have a histogram window, right? For now there's nothing displayed in it. But as soon as we clicked on the as soon as we created the histogram window, all those items, all those values that's inside of the volumetric folder in the results tab becomes visualizable, right? Suppose we are concerned about STOIIP, you can just click on it. And then later on, this STOIIP, the horizontal axis on this histogram plot are going to be STOIIP. And then at this step, we can sort of click on those cases, right? So for all the different values of the major range drawn from our random sample, these 5 cases actually gives us almost identical STOIIP, right? So by changing the major range, it's not going to change the STOIIP by a significant amount. You can just see that. So for all those 5 cases, it's actually giving us the same STOIIP value, right? And then let's look at if the minor range is going to change anything. No, it's not going to change anything, right? So it means that the STOIIP is not a value that's kind of sensitive to different values of the different cases, right? The different values of the major range or minor range, right? And of course, you can also display other values that you might be interested in. For example, GIIP, right? So for GIIP, you can sort of see some small variations, right? Was it caused by? Okay, so both major range and variable. Okay, so minor range is not going to change GIIP, right? Yeah, it's not going to change GIIP, but the major range changes in the major range is going to give you some kind of variation, right? But it's still very small variations. You don't even see sort of changes in the significant digits, right? So it's again, GIIP are not sensitive to variations in major range or minor range, right? If you sort of display both STOIIP and GIIP, yeah. So yeah, that might be a good thing, right? Because it's not changing too much, right? But it may be not. But maybe that's not exactly what you expected, right? So if you change the major range and the minor range, you may expect some changes, right? But the reason that it's not making any changes is because the major range and the minor range was specified for the background phase. That's the background floodplain. Background floodplain has a kind of a it's not the kind of a it's not the it does not belong to the it does not belong to the sand or channel sand or levee sand, that kind of phase that could have a big effect on those values, right? On those STIIP or GIIP values. Again, you can sort of look at maybe HCPV oil, HCPV gas, right? And so lots of values are kind of on top of each other. So it's kind of lots of columns are kind of on top of each other. So it's kind of difficult to judge. Right. So let's try petrophysical model. Try petrophysical modeling. And this is actually for the porosity model, right? This is for the porosity model. So let's change this one to major DIR pore, right? And then change this one to minor DIR pore. And then okay. And now we have 4 values, right? 4 variables. So again, let's use triangular. So let's give like a 3,500, 5,000, and then 6,000 maybe. And then for this one, let's give still a normal distribution, maybe 700. And then standard deviation 100. And then sensitivity, let's do fewer number of simulations. Let's give like 2 simulations per variable. And then Monte Carlo simulations. Okay. Oh, I forgot to click on run. Test still okay. Let's run it. So it's going to take a while to run the 8 simulations, right? And later on, so histogram is just one of the ways for visualizing the uncertainties, right? And there's also another kind of visualization called a tornado, right? Tornado graph, right? Which is also provided by Petrel if we would like to explore how to actually use the tornado app. So it actually has created a new folder. So this is for sensitivity, and then this is sensitivity underscore 1, right? This particular folder is going to hold all the tests, all the 8 cases that we are running right now. So you can imagine there's going to be 4 subfolders inside of sensitivity underscore 1, right? And one is for variable major range. Another one is going to be for variable minor range. And then there's a third one is going to be for variable minor DIR, a major DIR pore. And then there's going to be another folder that's for variable minor DIR pore, right? And inside of each of the folders, there's going to be 2 cases, right? Two volume calculation cases. But this time we're supposed to actually see some stronger variations because we're actually changing the porosity. We're actually sampling the porosity. We're sampling the variogram. We're changing the variogram of the porosity. So it should give us some, at least some level of changes. Now the simulation is done. So let's close this dialog box and then look at what's actually underneath sensitivity 1. Right, so we've got like four different variables, right? So again, if we would like to examine the values that's being tested or tried by the simulations, by the 8 simulations, we can sort of look into this particular table. And again, if we would like to actually look at the histogram, say for STOIIP, right? And then we can just, and then let's look at if it's going to change. No, it's not going to change with major range. We have already known that, right? It's not changing. Let's look at it. Yeah, we've seen some kind of variation, right? It's not a big oh, it's actually quite big, right? It's 1.218 10 to the 8th power. And then this is 1.226 10 to the 8th power. So STOIIP does have a quite big change for when you actually sort of consider the major DRR pool, right? That's the range of the variogram, the major range of the variogram for the porosity. Right? And then this is a minor. Right? Again, the changes are noticeable, right? So let's put all of them on it. Right. So that's gonna give us some idea about what the STOIIP actually is sensitive to, right? That's one. So this kind of sensitivity analysis is actually quite useful for us to actually understand what are some of the major control parameters in our entire process. If we look at the GIIP, that's a GIIP. So GIIP has an even wider range of variations, right? So, and then another diagram that might be useful is called the tornado. It's called the tornado plot window, right? And so suppose let's still look at STOIIP, and then let's select all the cases in this particular sensitivity test. Then it's going to draw the tornado diagram, right? It's going to tell us So major DR pore is going to have this kind of huge uncertainty, right? And then minor DR pore, it's going to be a very small thing, very narrow, right? And then major range, it's not going to change anything. So minor DR, compared to those minor range and major range, the major range and minor range for the porosity actually has a lot more sensitivity to the. I mean, S2RIP is kind of a lot more sensitive to the porosities, right? To the porosity, major range and minor ranges, that kind of thing. Let's close this window. And now let's look at what's actually inside of the data analysis button, right? We have skipped this button. Right? But let's look at it. What's actually inside of it? Let's just sort of have a very brief description about what's actually inside of it. So again, for the data analysis part, usually it's actually applied on those upscaled logs, right? For the upscaled logs, we have like 3 different properties: fluvial phases, porosity, and permeability, right? So usually we do analysis on fluvial phases, on phases logs first, right? And then we can select the different zones. For each different zone, we have to do a separate analysis, right? And so if we actually click on this lock, it's going to allow us to actually make changes. There are for this particular zone, most of the phases is actually black background flat plane, right? It's got like a 99.4%, and then we have 4 different tabs: proportion, thickness, probability, and variogram, right? Usually, for proportion, it's relatively easy. So if we actually fit active or curve, so if we click on it, that's gonna sort of try to actually fit the data that's actually on the. Maybe this is not a very good layer. Let's change it to a different layer. For example, let's do tarbert 2 to top tarbert, and then click this one, right? So if you look at these 2 panels, for the vertical axis, it's called a layer, right? It goes from like 20 to like 30, so we have like 10 layers, right? These 10 layers, the number of layers that we are seeing on this vertical axis is exactly the number of layers that we created when we were doing structure modeling. So during the structure modeling, one of the buttons is called layering, right? If we click on it, so we are looking at tarbert 2 to top tarbert, right? It's tarbert 2 to top tarbert, tarbert 2 to top tarbert, and the sail thickness was like 4, right? And then because we specify this sail thickness, follow base, that kind of thing, so it's going to generate, for this particular zone, it's going to generate this kind of 10 layers, right? It's going to generate this kind of 10 layers, and then for each of the layer on the upscaled logs, that's sort of the proportion of different phases. So for the 24th layer, the proportion of crevasse splay sand is like the whole thing, right? And then for the next layer, 25th layer, it's all levy sand. And then the next layer, it's got some portions of channel sand, and then some portions of levy sand, and then some portions of crevasse splay, right? And then that's the color is basically just telling you the phase. And then what we can do is to actually click on this button to fit active all curves to a linear regression, right? Or we can click on this one, fit active all curves to histogram. Right? This is actually a better choice. Actually, it's a better choice, right? And then the proportion curve. So this is actually the proportion estimated from the upscaled logs, right? And this is actually the proportion curves that's going to be used to actually control the proportion of the different phases on the fluvial phases model that's going to be used to populate the entire 3-dimensional mesh, right? And then if we don't like this kind of rough distribution that's estimated from the histograms, we can try to smooth it a little bit, right? It's going to give us, by clicking on this button, it's going to smooth the proportions, right? And we can actually try to do this thing. This is for background flat plane, right? And then once we have fixed this particular proportion, we can click on the lock to prevent further changes. And then we go on to the next one, right? And then sort of do another fit, and then maybe smooth it a little bit, right? And then sort of we can sort of do this kind of thing for like each of the different phases, right? So that's basically allows you to actually specify a proportion curve for the different phases inside of each of the different zones, right? And this proportion curve can be actually used for generating the model, for generating the phases model for these 4 different phases inside of this particular zone later on, right? If we choose some kind of algorithm, for example, Gaussian random function simulation, that kind of thing, or some kind of Kriging algorithm, it's or some kind of simulation algorithm which will take those proportion curves basically. And then the next tab is called thickness. For now, the bin interval is like too large, right? It's 10. Let's change it like 1 or something. 1. Then select all, right? And then it's going to tell us the horizontal axis is going to be the thickness, and then the vertical axis is going to be the percentage. It's going to be the percentage for all the number of cells that's penetrated by the whales. For all the kind of upscaled whale log, the cells in the upscaled whale logs, what's actually the percentage for each of the thickness and for each of the phase? This particular histogram is not going to sort of allow you to actually change anything or configure anything, right? But it's a kind of useful thing to examine or to look at and to understand how the whale log is actually distributed for how the upscaled log data is actually distributed, right? That's thickness tab. And then we also have probability tab, right? Probability tab. The probability tab allows us to actually configure the probability of the different phases based upon a different attribute or secondary attribute. So suppose we choose porosity maybe, but it's not a good idea actually, because later on we're going to use phase to control porosity, right? Right. If you click on this button, then it's going to tell us that. So the horizontal axis is going to be the secondary attribute. That's porosity, right? And then if we sort of look at the curve, then, for example, if we look at this particular point, at this porosity value, that's 0.1537118. At this particular porosity value, the probability for having this channel C in the phase is like close to like 0.1 or 10% or 12% or 11%, that kind of thing, right? And then the probability for having this kind of Levisian phase is going to be like close to like it's this kind of range, right? And then the probability for having the Krabbersy split end is going to be like that, right? That kind of range. So again, you can estimate the probability curve in this particular dialog box, right, based upon the porosity. Right. Of course, you can choose other properties as the secondary attribute. Maybe some other attribute is kind of more indicative about the particular phase, right? And then you can also try to smooth it, right? And once we have so let me look at channels in, right? So maybe smooth it. And then once we want to keep that value, and then sort of smooth it again. So once we have done selected, once we have come up with a curve that's kind of more realistic, then later on when we actually try to create the phases model for the entire 3-dimensional mesh, we can use this probability curve. We can use this probability curve to actually control the simulation process. And then we have one last tab, that's variograms, right? That's the variograms. And actually, to understand the variograms, we will need some understanding about geostatistics, basically, right? So how do we actually make these kind of changes, right? So how do we actually, so vertical direction, major direction, minor direction, what they actually mean, right? So these are actually the results of our fitting process. And then we are doing our fitting inside of this kind of window. So if we actually drag those boxes, we can also rotate it by some angle, right? And then so we can make adjustments to it. So as we actually drag these boxes, we're gonna see this kind of a change in the semi-variogram, right? So the horizontal axis is actually the distance between two neighboring so the basic idea of this kind of variogram analysis is sort of try to actually come up with a kind of some kind of model to indicate how the properties at two different points kind of vary or kind of correlate with each other with distance. So the correlation for 2 points that's kind of very close to each other is going to be kind of very similar. So the semi-variance is going to be very small, right? So that's why you see something that's kind of close to 0 right here. For some reason, it's not really. It's not really. Maybe it's using this video. And so as we actually drag these boxes, you're going to see those numbers actually change. The major range, the minor range, that kind of values actually change, right? This variogram thing is actually probably the most important or most time-consuming part of the data analysis process, right? So this basically plot actually this part of the plot actually shows you the variogram. So variogram is basically just a way for displaying how similar, how different two points are based upon the distance separating these 2 points, right? So close to the 0 means that the 2 points are kind of very close to each other. So the variance is like very small. So there's almost no difference between them. But as you move along the horizontal axis, the distance becomes larger and larger. So the semi-variance, the difference between those 2 points are going to become larger and larger, right? And so that's this vertical axis, right? And then if you look at this vertical axis, that's called a number of pairs. So the columns here basically are displaying the number of whale pairs, right? So we have like a 14 whales that actually have log data, right? So for every this kind of a distance range, how many whale pairs we have for that particular distance range, right? Distance range. So for this particular distance range, we have a lot more data pairs or whale pairs than other kind of data ranges, right? And then by dragging these boxes, we're actually basically just changing the major range. You can sort of see that, right? We're just basically changing the major range. So the major range is actually the horizontal distance from 0 to the vertical projection of this red box, right? And then by dragging this red box, we can actually try to fit this gray box, a gray curve. This gray curve is some kind of theoretical estimate, the regression, right? Regression result. And then the model is like controlled by this red box, right? We can drag this red box so that the blue curve actually fits the gray curve. And then that's going to give us the major range, right? And then we have minor range. We can actually do the same kind of thing, right? But because the minor range has to be sort of perpendicular to the major range, so it's not going to allow you to do any kind of rotation anymore. So you cannot actually change the direction of the minor range. It has to be perpendicular to the major range. But you can actually change its width, change the search range, that kind of thing. And then you can just try to sort of adjust the curves to fit the gray curve, right? And then you will be able to see, oh, there must be something wrong, I think. Minor range is supposed to be smaller. Again, we have just 14 whales, so it's not a really particularly good example for us to demonstrate this particular technique, right? So number of legs for now it's like fixed like 8, but maybe let's for the minor range let's increase to like 50. So that's gonna give us a lot more pairs, I think. So we have to do this kind of thing, and then vertical range, right? Vertical range, we haven't actually tested the vertical range yet, but we can do a similar kind of thing. Vertical range, say like give it a 100 or something. Oh, it's probably too big. We need to do this kind of thing, do this kind of a data analysis for all the different phases. This is just the background flat plane, right? And then we also have channels in, and then we have to do that whole thing again for channels in. And then we have to repeat the same process for leaves in. So, and then for crevice spacing, that kind of thing, right? So, and then we have to sort of repeat the entire process for every zone. So here we have like 6 different zones, right? And then we have 4 different phases, right? So it's 6 times 4. That's 24. 24 analyses, right? Going through this kind of step. So it's extremely time consuming, right? And if we have lots of data, then this kind of process can be quite fast, right? Because it's not too difficult to estimate those data. But if we have just a few wheels, just by rotating this kind of rotating the major direction or doing this kind of rotation in this kind of 360 degrees, it's a kind of it will be very, very tedious and very time consuming, right? And if that's the case, it's kind of important for us to actually understand the regional structure first. So one possibility is to actually look at the seismic attributes, right? If the seismic attributes actually has some preferred direction, right, and we can actually try to estimate those major range directions and values. We can estimate those parameters of the variograms from those seismic attributes, for example, right? But again, once we have actually finished doing all those data analysis, we can just click on OK, right? And then when we actually do the property modeling, right? For example, phases, we can actually use the data, use the result of the data analysis, right? Suppose let's change to that, and then if we unclick, and then we are going to have those buttons. This is called use variogram data from data analysis, right? We can just click on it. Then it's going to copy over all the results from our data analysis step, right? And then everything is going to work out, right? So those values, so this major direction range, 2A2.8 to A 1231.722 were actually determined by the data analysis, right? So if we, can I open the data analysis box again? Right, that's so this is from tablet 2 to top tablet, right? Tablet 2 to top tablet, and then the variogram for background flat plane, that's 2882.A2A, 2882.A2A, right? And then 1231.722, 1231.722, and then vertical is a 5.372. So if we have done the data analysis, we can just import the results from the data analysis by clicking these 2 buttons, right? Basically. This is just for phases, right? We also have to do this thing for porosity. If we have, so this is just for property fluvial phases, right? So we also have porosity and permeability. And for porosity and permeability, we have to repeat the same analysis, right? The only thing that might be different for phases analysis is that now you have these kind of transformations. So the purpose of these kind of transformations is actually to convert the distribution into more or less a Gaussian distribution or normal distribution, right? Doing this, so maybe input truncation, that kind of thing. Can I? No conditioning on phases. Let me choose a conditioning on phases. Right. Yeah. Can I insert one? So normal score, input truncation, and then directional data trend. Right? So let's do the input data truncation first, and then do a directional data trend modeling, and then convert it to normal score, that kind of thing, right? Estimate. It's not working. Right. That's the transformations, right? That's just transformations. And then we also have the varograms, right? That's the varograms. And then this is for just the one phase background, right? And then we have like three different phases here, right? For this particular zone. So suppose we switch to a different zone, top to phases, right? So it's like 4 different phases and then 6 different zones. And then how many properties? We got like a porosity and a permeability. That's like 48 analysis. We have to sort of go through this analysis for 48 times, actually, basically, right? So it's extremely time consuming, and it takes lots of research to actually use those capabilities correctly. And again, once we have done the data analysis for those petrophysical properties, when we actually try to create the models using this petrophysical button or petrophysical dialog box, we can actually use those. We can actually directly import those results in the results from the data analysis into the petrophysical modeling process. So that's pretty much everything that I want to say about those kind of petrophysical modeling or property modeling, right? Property modeling. So starting from the next video, we're going to start to work on the seismic data.